the past 10 years, Dixie Aerospace has made a primary investment into the metrology of reverse engineering. Our reverse engineering process and our close relationships with manufacturers has helped build a dynamic engineering team. Our engineers work closely with manufacturers and their engineers, which allows us to utilize years of experience and knowledge. The investment and focus in these areas has given Dixie Aerospace the tools required to produce quality FAA PMA-approved parts. Before the project engineer begins reverse engineering, they begin the stage planning by reviewing maintenance manuals and manufacturing catalog information. Maintenance manuals such as CMMs, OHMs, and IPCs are used to help the project engineer understand how their parts fit in specific systems and how those systems function for the aircraft operation. These manuals also provide repair and overhaul information on important part features which can be considered while reverse engineering. Manufacturing catalog data is researched to help the engineer understand who made the OEM parts. If the manufacturer has indicated any internal part number, the engineer can research this to typically find general dimensions specified by the manufacturer, such as bore diameters, outer diameters, widths, and materials. As detailed photos are taken of the parts and packaging, the engineer is determining which features will fall into the assembled measurement condition or the disassembled measurement condition. They utilize their training to begin laying out the test and computation worksheet, which is used to collect all the measurements obtained during the reverse engineering. A key question the engineers ask during this stage is why. Why are these parts boxed the way they are? Why are they greased or oiled? Or why do some surfaces shine differently than others? Never assuming is very critical in this stage, and all features will be measured using the most accurate machines in the lab. After the photographs have been taken, a high-precision scale is used by the engineers to weigh the OEM packaging materials and components. This scale can be read in 8 different units and has a removable casing around the scale balancing plate to control atmospheric disturbances. When the components have been weighed, they are taken to a cleaning tank and then brought back to the scale to be re-weighed. These 2 weight measurements are used to derive bearing grease and oil weights. The radial plate gauge was designed and manufactured by Dixie to measure the looseness that exists between the rolling elements and raceways. This clearance is a critical part of how the bearing will operate in the design system. The engineers will choose from a variety of calibrated weights depending on the size of the bearing. In this example, we're using an 11-pound weight. As the weight is placed on the rocker arm, it is transferred to a radial load on the outer ring. The dial indicator reads this radial play as the space between the inner raceway, outer raceway, and rolling elements as the weight is applied. The bearing analyzer is a machine that Dixie uses to simulate an in-operation test condition. This machine will collect a noise vibration signature from the bearing by the use of a high-sensitive ruby-tipped microphone that is placed on the outer diameter of the bearing. The engineer places each OEM bearing on the shaft spindle and then applies an axial force on the rings so no radial play is remaining. Then the bearing is spun to 1800 RPM, and the noise signature of the rolling elements and cage are captured and measured as anderons. This machine will categorize the frequencies produced by the bearing into low, medium, and high filter bands. Bearing manufacturers use standards to determine maximum acceptable limits on these filter bands. These limits indicate to users that the bearing components are running without defects. All OEM part samples are subjected to this operational test. After the Dixie PMA parts are manufactured, they are then run on this same machine to assist Dixie Engineering in their research and development towards OEM and PMA comparisons. The contact angle machine was another machine that was designed and manufactured by Dixie Engineering to perform an in-operation test. Contact angle is the angle between a plane perpendicular to the ball bearing axis and a line joining the 2 points where the balls make contact with the inner and outer raceways. After several inputs are entered into the machine software, an electric press is used to apply an axial load on the bearing, up to 225 pounds. The high-precision laser will count the ball separator rotations as it is carefully spun at a low RPM. The software will output a contact angle and a true rotational ratio, which will be used to calculate true contact angle once the bearing is disassembled. The optical comparator is a machine used for visual dimensional checks. The high-intensity light projects the image onto a larger screen to collect these dimensions. The Mitutoyo linear height gauge is a high-precision height measuring instrument featuring a 0.1 micrometer screen resolution. The slider can be moved up and down either manually or by the motor. In addition to the normal height measurement, the curved surface of the workpiece can be scanned with a constant measuring force by using the automatic constant pressure mechanism so that the maximum value, minimum value, and width in any range can be obtained. Circles can also be measured for shafts and holes features. The linear height gauge can also be used to create, execute, and edit part programs, take two-dimensional measurements, make tolerance judgment, perform statistical processing, and store and retrieve part programs or measured data to and from personal computers. The Mitutoyo SV C4000 form tracer was one of Dixie's early investments into the metrology lab. This machine uses a high accurate holography scale to carefully project the profile part scan. This scale is based on the interference phenomenon of diffracted light. After the part is mounted, the machine stylus is automatically lowered onto the part surface and then carefully pulled across the profile under the scan conditions set by the engineer. The included form pack software allows the engineer to carefully interpret the scanned data by placing points, lines, and circles over the data to determine the profile characteristics. The RAM optical instrument Starlight GX is a complete non-contact optical inspection system with interactive measurement capabilities. This machine is commonly used to collect measurements on plastics, small components, and non-magnetic part samples. Some of the features include a high-resolution digital color camera with zoom optics, accurate XY measurements to better than 2/10,000ths of an inch, an advanced image processor with automatic edge trace, and multiple field of view tools. As the engineers optically scan the part samples, the data is collected in the Starlight software, where features can be measured, such as points, lines, circles, and positional characteristics. The Mitutoyo SJ500 Surface Finish Tester is utilized to collect all surface finishes. This machine supports 43 types of analysis parameters, complying with surface roughness specified by ISO and JIS standards. Some of the common contour analyses performed by this machine include area, circle, angle, coordinate difference, step, and inclination. Dixie utilizes a calibrated hardness tester to test for surface hardness requirements. This machine is used to collect preliminary hardness data before the components are sent to an independent metallurgical testing facility. Each part sample is checked in either the HRC or HRB scales. These hardness checks help the engineer determine heat treat conditions that may exist. The heat treating condition is an important feature which helps indicate what type of environment the parts are intended to be stable for operation in. Dixie outsources all material composition testing to an independent lab where they also check surface and subsurface hardnesses in addition to the material chemical compositions. The Brown & Sharp and Mitutoyo coordinate measurement machines are used for all reverse engineering that require three-dimensional measurements. The CMMs are pneumatic and electric-driven machines with interchangeable ruby-tipped styli. After parts are mounted, the CMM is programmed by the operator to carefully trace all desired profile features. The CNC-driven machine utilizes PCDMIS and SolidWorks to interpret the part shape and feature locations. These two machines accurately trace profile forms, find hole locations, and carefully collect all geometric dimension and tolerancing requirements specified by the project engineers. The Mitutoyo Round Test RA2200 is a CNC-driven machine that provides high accuracy, high speed, and high performance roundness measurements. This machine is extremely diverse and can also quickly gather cylindricity, roundness, concentricity, radial runout, perpendicularity, parallelism, flatness, and many other combinations. This machine sits on an air leveling table to prevent any ground disturbances and has a rotational accuracy of 0.02 micrometers. The end-shake gauge is a very unique tool designed to measure the space that exists between the roller ends and the guide flanges that hold them in place. This feature can be very critical in main engine shaft assemblies and can only be measured by accurately leveling the roller ends and guide flanges with respect to the dial indicator. After the rollers have been leveled, the machine is designed to control the perpendicularity of the vertical travel with respect to the machine table. This travel is then captured using a high-precision 20 micro-inch dial indicator. Dixie Aerospace has established itself as a leader in FAA PMA development. Our state-of-the-art equipment and dedicated engineering and manufacturing staff helps the Wencor Group develop more than one new PMA part each day.